Hello viewers on YouTube. In this video tutorial, we are going to consider complex number, typically in rectangular form. From the introductory video, we stated that complex number in the rectangular form carries this pattern: z equals a plus bi, or sometimes might be expressed as z equals x plus yi, where a and x tends to be the real part of the complex number and b and y tends to be the imaginary part of the complex number. Now, it is important to point out that ordinary rules of algebra still applies to complex number. However, there are some particular attention that you have to pay to some facts. And what are these facts? You need to understand that while doing operation on complex number, either you are adding or subtracting complex numbers, you have to treat the real and imaginary parts separately. You can't treat them together. Are we together? So you have to treat them separately. This is a very crucial aspect you have to put into account while doing the operation on complex number. Now, secondly, we said that the root of -1 from the introductory video, this is equal to I. Now, what will now be I squared? I squared, in notice, will simply be equal to -1, because by the time we take the square of both sides of this equation, we are left over with this. Now, what about I to the power of 3, which is also called I cube? Well, from algebra, we know that I cube can be expressed as I squared multiplied by I. However, we said I squared is -1. So we have -1 multiplied by I. And this results in -I. So I cube is equal to -I. Now, similarly, if we have I to the power of 4, this will simply be equal to I squared multiplied by I squared. I squared is -1, I to the power of 2 is -1. And by the time we find the product of these two -1s, we are left over with 1. And this pattern continues like that. You just keep on breaking and continue your substitution. So these are the things we are going to put into account as we proceed forward. So let's move into the process of adding and subtracting complex number in a rectangular form. Let's begin with some examples. Example number 1. Given that z1 is equal to 4 plus 3i and z2 equals to 5 minus 2i, find z1 plus z2. So, if you know what to do already, feel free to pause the video and figure this out yourself. And after that, you can unpause it and check if you have done the right thing. So let's begin. z1 is 4 plus 3i and z2 is equals to 5 minus 2i. The goal is just to find the addition of these two complex numbers. And to add two complex numbers, just pay attention to the real and the imaginary part of the complex number as you are treating these separately. So that means that we are to add the real part of the two complex numbers together and do the same thing for the imaginary part. So what will be 4 plus 5? Well, notice that will result in 9. So therefore, z1 plus z2 becomes a complex number with the real parts to be 9 units. Now about positive 3i plus negative 2i. Be sensitive while dealing with the imaginary parts. Let's bring it out. Positive 3i plus negative 2i. And then we have positive 3i. Positive times negative 2i. When we expand the bracket, we have negative 2i. And right now, we have positive 3i minus 2i. Left over is just 1i, which is the same as positive I. And that gives us a result to the sum of the two complex numbers. And that's the solution to example number 1. And at the same time, that's how to easily add two complex numbers. On to example number 2. Using the information provided in example 1, find Z1 minus Z2. So this simply means I have to bring back the information given to us in example 1. However, the only thing we need is just Z1 and Z2. So let me write it beside. We said Z1 is equal to 4 plus 3i. Also, we said that Z2 is equal to 5 minus 2i. So to find the difference between these two, all we need to do is just to do the same thing like what we did earlier. But this time around, the sign is a subtraction sign. So Z1 minus Z2 becomes, so this is coming first, followed by this. 4 minus 5 gives us negative 1. And for the imaginary part, like I said, always write it out to avoid silly mistake. So we have positive 3i, the minus negative 2i. By the time we do the subtraction, we have positive 3i plus 2i. You know, when this expand, left over is positive 2. And this results in positive 5i. And we jam that with this negative 1 and have the difference between the two complex numbers. And that also gives us the result to example number 2. On to example number 3. Using the information provided in example 1, find Z2 minus Z1. So if you could recall, we said Z1 is equal to 4 plus 3i. And we said Z2 is equal to 5 minus 2i. So right now, we want to find Z2 minus Z1. Keep in mind, the order is very, very important. It's relevant. You understand? So Z2 is coming first. This amount, it means we are doing the operation in this manner. So 5 minus 4, that gives us 1. So Z2 minus Z1 would be equals to 5 minus 4, gives us 1. Now negative 2 minus positive 3. What would that be? So we have negative 2 minus positive 3, I. I is the actually. We have negative 2i minus 3i. That gives us negative 5i. So that gives us the solution to example number 3 as well. So Z2 minus Z1 is 1 minus 5i. By now you should have been following up with the logic and the process of adding and subtracting complex number in a rectangular form. It's kind of straightforward. There's no any issue. On to example number 4. Using the information provided in example 1, find 2z1 minus 3z2. Now each of these complex number has now been multiplied by a scalar. So how do you handle this kind of situation? So here's what we have to do. Just like before, we said z1 is equal to 4 plus 3i. And at the same time, we said z2 is equal to 5 minus 2i. Perfect. Now to find 2z1, all you need to do is to multiply these two values by whatever is multiplying the entire complex number. In other words, you can just write this and just expand the bracket. So whichever way works best for you, you are good to go. So I'm multiplying 2 with the reparts, and the product of 2 and 4 results in 8. And for this 3i, when I multiply 2 with it, we have 6i. So that's 2z1. So let's repeat the same thing for z2. So 3z2. By the way, you can do minus 3z2. Nobody will question you. But don't forget, if you do minus 3z2, when you want to apply the equation, you're adding them. So it's better we just do 3z2. Perfect. So 3 times 5 gives us 15 for the repart. And 3 times negative 2 gives us negative 6i for the imaginary part. I is still there. Perfect. Now the goal is to subtract. We want to subtract the two values. As we have been doing so far, we are still going to subtract separately. So 2z1 minus 3z2 becomes 8 minus 15. That gives us negative 7. And positive 6 minus negative 6. What would that be? Plus 6i minus 6i. That gives us plus 6i plus 6i, which becomes 12i. So that will be plus 12i. And this is the result to 2z1 minus 3z2. And that's how to easily multiply scalar with a complex number before applying any operation on it. Perfect. On to example number 5. Using the information provided in example 1, find z1 times z2. So we do multiply two complex numbers as well. And your question might be, how does it work? Let's see. So we are still using the same information we have been using. z1, that's 4 plus 3i, and z2, that's 5 minus 2i. The goal is to find the product of the two complex numbers. To multiply two complex numbers, you expand them as if you are expanding two binomials. What I will say makes sense. Enclose each of them within the parentheses. So the first one is 4 plus 3i, and the second one is 5 minus 2i. Then you expand this bracket and simplify your result. At the end of the day, once you have it in the simplest form, you have your final answer. So let's do that. 4 times 5 gives us 20. Then again, we did for the other one. 4 times negative 2i, we have negative 8i. Now positive 3i times 5 gives us positive 15i. And finally, positive 3i times negative 2i. What would that be? Let's just do the values first. Plus 3 times 2, that's minus 6. Now I times I squared. But do you remember what we said I squared is earlier? Thank you. We said it's the same thing as negative 1. So instead of I squared, let me put negative 1. I'll put together. Very good. So now let's simplify a little bit forward. We have 20 negative 8 plus 15. That gives us positive 7 plus 7i. Negative 6 times negative 1 gives us positive 6. And since these two are constant value, then they are addable. 20 plus 6 gives us 26 plus 7i. And then we have our final answer to example number 5. And that's how to easily multiply two complex numbers. Now you might have a question such that you might be wondering, do we divide complex numbers as well? Well, the answer is absolutely yes. We do divide complex numbers. But to succeed in dividing complex number, at this point, there's something you have to be familiar with first. And that's what we're going to put into account before we now consider going over an example that involved the division of complex number. And what exactly is that? We call it the conjugate of a complex number. So what does that mean? Consider a complex number z that is in the rectangular form x plus yi or iy, regardless, it doesn't mean anything. Now, the conjugate of this complex number z carries two notations. Sometimes it might be expressed as z with a bar on top it, or another time it might be expressed as z with an asterisk on top it. Well, in either case, wherever you see this symbol, notice that they are referring to the conjugate. And what does it mean? It's the same complex number, but with different sign being attached to the imaginary part. So generally, we negate the imaginary part to get the conjugate of that complex number. So since this is positive, then the conjugate will be x minus yi. In other words, the conjugate is the same complex number but with different sign between the real and the imaginary part. Are we together? So simply means that if I have another complex number z, which is of the form x minus yi, then its conjugate z bar or z asterisk will be x plus yi. So that's how to easily identify or find the conjugate of a certain complex number. So I'm using letter. Let me use numbers. So let's say z is equal to 2 minus 3i. Then its conjugate will be 2 plus 3i. Straightforward. Are we together? Perfect. Now that you know this, it's easy for us to simplify divisions of complex number. So on to example number 6. Express the following in the form a plus bi. Now when you have complex number to be divided by themselves, though this is a real number divided by a complex number, regardless, once you're having a fraction, generally speaking, what we do is that we pay attention to the denominator. 1 divided by 1 plus I. Now see, the denominator is a complex number actually. So as long as the denominator is a complex number, the next thing to do to simplify this kind of problem, is that you will multiply the top and bottom, that is the numerator and denominator of these compound complex number. You will multiply them by the conjugate of the denominator. So if the complex number is 1 plus I, what will be the conjugate? Thank you. That will be 1 minus I. So you multiply it with the top and bottom. So we have 1 minus I divided by 1 minus I. We are multiplying to the top and bottom. Now you can see that this can cancel and becomes 1. And 1 times this thing gives us back. So we are doing this so as to be able to simplify this expression, and at the same time to get rid of the I at the denominator. You understand? The process of this is called rationalization, if you are wondering what the process is called. So let's begin expanding. So 1 times this entire expression gives us back. So we have 1 minus I divided by. So let's do this one. So what I like to do is to put them within the parentheses. It's very easy for you to get the expansion. 1 minus I. So 1 times 1 gives us 1. Okay. 1 times negative I gives us negative I. I times positive 1 gives us positive I. And I times I, positive I times negative I gives us negative I squared. Don't forget, y squared is negative 1. So we have 1. This can cancel. They are of opposite sides, right? Okay. Minus. So I squared we said is negative 1. Negative 1. Okay. Okay. Now this can multiplies. And then we have 1 plus 1 equals 2. So therefore, the denominator has reduces to 2. Now the question asks us to express it in this form. The next thing we can do just to simplify this is just to put the denominator for the individuals at the numerator. So this becomes 1 by 2 minus I by 2. I think now in that form. You can see have it as 1 by 2 minus half I. Simply just the best. Where A will be half and B will be negative half. So that's it. So that's the solution to example number 6. Now you know we said that the process of simplifying a complex number that are dependent themselves is called rationalization. There's also something called realizing or realization. This process is a technique we use to convert a complex number into a real number. You see, though there might be some coincidence whereby by the time you do the operation at the end of the day, you will have a real number, a complex number with a mute, you understand? But this realization process, it's the main concept we use to convert any complex number into a real number. So how does it work? Let's look into that as well. Consider a complex number z that is equal to x plus iy or yi. Let me use yi. Okay, Q. We know that the conjugate of this complex number would be x minus yi. Now, can we do the product of these two complex numbers? The product of z and its conjugate, what would that be? Well, we said the best way to do it is to enclose them within a parenthesis. So this becomes x plus yi, then multiply by x minus yi. So let's expand. X times x gives us x squared. X times negative yi gives us negative xyi. And positive yi times x gives us positive xyi. Okay, and finally positive yi times negative yi, that gives us, let's do the coefficient first, plus y times minus y gives us minus y squared, then I times I gives us I squared. Now these are unlike terms, they can see them themselves. We now have x squared minus y squared times I squared is negative 1. Then we have x squared minus y squared times negative 1 gives us positive y squared. As you can clearly see, there is no more high terms, and x and y are just ordinary values, which by the time you square them individually and add them together, we're going to just have an ordinary value, which is a real number. The process of doing this is what called realization. So if you are required, or if you are asked to realize a certain complex number, what they want you to do is to multiply that complex number with its conjugate, so you can have a real number. Are we together? Perfect. So let's proceed forward on to example number 7. Simplify 4 plus 3i all squared divided by 1 plus 2i. By the way, if you would like to check this question out, feel free to pause the video and try it out. And after that, you can just unpause it and see if you have done the right thing. So before I do editing, I would like to simplify this numerator. So what will be the square of 4 plus 3i? Well, in algebra, we know that this simply means 4 plus 3i is multiplying itself 2 times. But from our knowledge, we already know how to expand two complex numbers. So let's go ahead. 4 times 4 gives us 16. 4 times positive 3i gives us positive 12i. 3 times 4 gives us positive 12i again. And finally, plus 3i times plus 3i. Don't forget, you do the coefficient first. 3 times 3 is 9. Plus 9 times I times I is I squared. Multiply by minus 1. This is equals to 16 plus 12i are addable. We have 24i. Then when we multiply this, we have minus 9. What is the addition of 16 and minus 9? Well, that will result in 7 plus 24i. So that is the simplification of the numerator. So now it's easy for me to replace. So the expression has been reduced to 7 plus 24i divided by 1 plus 2i. At this point, I can rationalize. To rationalize, we find the conjugate of the denominator and then multiply with the top and bottom. The denominator is of the form 1 plus 2i. Then its conjugate becomes 1 minus 2i divided by 1 minus 2i. Again, another expansion. But I don't want to put within the parentheses this time around, but instead show it with some pattern. 7 times 1 for the numerator gives us 7. Again, 7 times negative 2i gives us negative 14i. Plus 24i times 1 gives us positive 24i. And plus 24i times negative 2i. Let's do plus 24 times minus 2 fourths. That gives us negative 48. Then I times I, negative 1. Perfect. Eventually divided by 1 times 1 gives us 1. 1 squared is still 1, by the way. 1 times minus 2i gives us minus 2i again. And this times this gives us plus 2i. And finally, 2 times minus 2 gives us minus 4. And I times I is still minus 1. Perfect. Hope you're following. Good. So let's proceed forward. Now, let's add these two terms. Minus 14i plus 24i. That results in plus 10i. So we have 7. I go to 9. 7 plus 10i. Now minus 48 times minus 1 gives us plus 48. Divided by, these cancels on like terms. We just have 1. Minus 4 times minus 1 gives us plus 4. And this simplifies to 48 plus 7 is 55 plus 10i divided by, then 1 plus 4 is equal to 5. Can we simplify more forward? Yes, we can. Let's factor out 5 at the numerator. And doing that, for the 55, we are left with 11. And for the 10i, we are left with 2i divided by 5. Then the 5 can cancel out. And final answer in this case is 11 plus 2i. And that's the solution to this example number 7. I hope you got that. On to example number 8. Simplify 4 minus 2i divided by 1 plus I all squared. Now, you can clearly see that the second question is kind of similar to the previous one, but this time around we are not having the square at the denominator. Well, just like what we did earlier in the example 7 question, we are going to do the same thing here. Let's expand the denominator first and then simplify it and have it in the rectangular form. Then after that, you can find the conjugate and proceed on rationalizing. So what will be 1 plus I all squared? Well, we said that will be 1 plus I times 1 plus I. And 1 times 1 gives us 1. 1 times I gives us plus I times 1 still gives us plus I, and I times I gives us minus 1. These are addable, these are unlike terms, so it cancels. And then we have 2i for the expansion. Well, that's kind of straightforward. No more repart, just imaginary. Well, that's good. Therefore, the expression has been reduced or compressed to 4 minus 2i divided by 2i. Perfect. Now, you might be wondering, now, how do we find the conjugate of these single term at the denominator? So, as long as what you're having at the denominator is not a rectangular form complex number, then the conjugate will still be these imaginary. Just take this I, understand? Just take the I, okay, along with the stuff right here. Understand? If you do 2i, you will still get the same answer as I, regardless. So the choice is yours. You understand? But let's use I. So we are multiplying the top and bottom by I over I. The main reason we are rationalizing is to get rid of this I at the denominator. You understand? That because that's the meaning of rationalization. That's why I said realization is to get rid of the imaginary part in that complex number, while rationalization is to get rid of the imaginary part at the denominator. Are we together? Perfect. So now I times 4, 4i. Then minus 2i times I. Let's be careful. You know, this is like 1i. So 1 times minus 2. That gives us minus 2 times I times I minus 1. Perfect. Just be careful. Don't always write it out, because you might not know, you might make mistake. Just always write it out. These will clear all your doubts. Divided by, so 2i times I as 2 times, just like 2 times 1 again, that's 2. I want to get rid of this. 2, then I times I is minus 1. Good. So we have 4i. So minus times minus 2 plus 2 divided by minus 2. So let's factor out 2. We have 2i plus 1 divided by, this is 1 minus 2. The 2 cancels and the minus comes inside. Finally, we have our final answer to be minus 2i minus 1. So that should be the solution to the simplification. And that results in the solution. So example number 8. On to example number 9. Find the square root of negative 8 plus 6i. To find the square root of a complex number, here are the approach. First, you need to know that the root of a complex number will give back a complex number. If we want to convert a complex number to a real number, then we have to do the techniques I explained earlier, which is realization. Any other operation that you do on complex number, you will still have a complex number back, except some unusual scenario, or if a coincidence happens, whereby at the end of the day, after the operation, you have a real number. Otherwise, the result will always be a complex number. So, let the root of this negative 8 plus 6i, let it be z, since we know that it will still be a complex number. And we said z is always of the form x plus yi. So if the root of negative 8 plus 6i is equal to z, this simply means that the root of negative 8 plus 6i will be equals to x plus yi. Incredible. Now, upon taking the square of both sides, we calculated that this root can get rid of. And then we now have, I've not put this out. Okay, fine. Good. Now, taking the square of both sides, we can clearly have minus 8 plus 6i to be equals to the square of x plus yi all squared. Good. Now let me flip this. I want to flip the position. Well, since the equal sign is correcting them, nothing will change. X plus yi all squared equals negative 8 plus 6i. Okay. Now, let's expand this one. We have x plus yi times x plus yi equals negative 8 plus 6i. So x times x, would that please be enough? I think so. Would be x squared. X times positive yi gives us positive xyi. Again, positive xyi plus xyi. And finally, yi times yi would gives us negative y squared. So the I is gone. I times I is minus 1. And multiply it with positive y squared gives us negative y squared. Are we there? Perfect. Now let's sit down. Y squared minus y squared and x squared has no I terms. Let's bring them together. And then we have x squared minus y squared. And let's have these terms with with I together. That gives us plus 2xyi equals to 8 minus 8 to say plus 6i. Now, if this is to be true, understand, we are saying equal sign. If this is to be true, if this equation we are having now, if it's going to be true, then this simply means that this real part must also be equal to the real part of this one, because we are comparing the sides. Otherwise, that means that equal sign that is there is not meant to be there. But if it's equal sign that has to be there, it means the real part of what we are having at the left hand side, which is x squared minus y squared, must also be equal to the real part we are having here. And that's exactly what we are going to do. So we are going to set x squared minus y squared to be equal to minus 8. Let that be equation 1. Similarly, the imaginary part will also be equal to the imaginary part, which implies that 2xy will also be equal to 6. Equation 2. Our goal now is to find the value of x and y with the help of these two equations. One is so this is just a simultaneous linear and quadratic equation, as you can see. Okay, so we just need to make some substitutions. So let's solve for a certain variable from equation 2 and get the third equation. Let's solve for x. Upon dividing both sides by 2y, we can clearly have the value of x to be equals to 6 divided by 2y, which reduces to 3 over y. Okay. Now, instead of x, let's put 3 over y. Don't forget, this equation is equation 3. So now I need some space. So now for substituting 3 over y as x in equation 1, we have 3 over y all squared minus y squared equals to 8. Why am I mentioning 8? Minus 8 to say. Now, if I dispute the square, we have 9 over y squared minus y squared equals to minus 8. So the square will come inside each of them. Q. Now, to make this straightforward, let's try to make some other substitution. So let's assume y squared is equal to b. Then this equation entirely becomes 9 over b minus b equals to minus 8. Now we can multiply all through by b. And then we have 9 over b times b minus b times b equals to 8 times b. So these cancels, gone. Minus b times b is b squared, and minus 8 times b is minus 8b. So let's get that. I hope you are following the steps. And this is the same way you are going to be solving for the square root of a complex number. Are we together? Perfect. So we now have new equation in the form 9 minus b squared equals to minus 8b. So let's set everything to be equal to 0 and then solve quadratically. So let this comes likewise this. I want the coefficient of the dividend term to be positive. So we have b squared minus 8b minus 9 equals 0. When the negative b squared comes, you have positive b squared. You understand? Similarly, when the positive 9 comes, we have negative 9. In other words, you can just add b squared to both sides and at the same time subtract 9 from both sides. Now at this point, we need to factorize what two numbers multiplies to negative 9 at the same time add up to minus 8. Well, we already know the answer. That will be 9 and 1. And this will simply be minus 9 plus 1. The product of these two numbers gives us minus 9. And at the same time, when we add them, we have negative 8. Some of you might be wondering, how did he get minus 1 or minus 9 and 1? Well, all you need to do is to find all the factors of this one. So, what are the values that when you multiply them by, when you multiply them together, just two values, you are going to have 9. Well, you might be like, how can I be thinking what these values will be? Well, this is logic. This is the logic. You start from 1 and that value. 1 times any value gives you the value back. The next thing is you now proceed to the next number after 1, which is 2, divided by this thing. 2 can go in 9. Leave that one to the next one. 3. 3 can go in 9. How many places? 3 places. Then, that 3 you are using to divide, the result you are going to have, if you multiply it with what you used to divide, you will get what you get back. 3 times 3 gives us 9 again. Then you move to 4. 4 does not work. 5 doesn't work. 6 doesn't work. 7 doesn't work. 8 doesn't work. You get to 9. But 9 has already shown up. Once you get to a point whereby that point is already included, you stop. Now, you're now going to test on these two. These are the two you'll be using. Are we together? So this can never work. There's no way I can add 3 2 times and have 8. So definitely, this is the one to use. Once you know the two values to use, then you can now determine the sign to assign to them. So it's kind of straightforward, but more practice is required. So you don't need to waste time before getting those two numbers. So we say we're using minus 9 and positive 1. So let's attach b to it and then replace. Then we have b squared minus 9b plus b minus 9 equals 0. Then factoring out b from here and factoring out 1 from here, we have b in the bracket of b minus 9 plus 1 in the bracket of b minus 9 equals 0. So we can fix the GCF at this point and have b plus 1 multiplied by b minus 9 equals 0. So therefore, the value of b will be equal to 1, or the value of b is equal to 9. So by the time we set each of them to be equal to 0. Now don't forget, we made a certain substitution earlier, so we need to reverse it back. We said y squared is equal to b. So we need to find the value of y. It means y squared is equal to, okay, this should be negative 1. By the time the positive 1 comes all the way to this side, that will be negative. Thank God I quickly realized minus 1. Then similarly, y squared will be equals to 9. Now by the time we take the root of both sides of this one, we can clearly see that y will be equals to the root of negative 1. It gives us I. But y is a real number. And besides, there's no number you can square that is a real number and you still have negative. The square of a real number always gives us a positive number. So we can clearly ignore this. This is invalid. Y is a real number, not a complex number. As from the beginning of the example that we are solving, by the time we detach them, we realize that x and y are real numbers. Okay. So this is gone. Pay attention to this one. Take the root of both sides, y will be plus or minus 3. And using these two values, we can get the value of x. Well, can I remember the third equation? Earlier we said equation 3 is such that x is equal to, I think, 3 over y. Did I got that right? Yeah. So that's when y is positive 3, we have 3 over 3, that gives us 1. And when y is negative 3, we have 3 over minus 3, gives us minus 1. So these are the corresponding values of x. Now that we have these two values, then we can simply make our final conclusion that the root of minus 8 plus 6i, the root of minus 8 plus 6i would be equals to, so when x is 1, y is 3. So that will be 1 plus 3i, or when x is minus 1, y is minus 3. So minus 1 minus 3i. So these are the two values for the root of negative 8 plus 6i. So that's how to easily find the square root of a complex number.